subtraction games.
Thank you, Dr. Z. I'm not just going to speak about subtraction games, I'm speaking about aperiodic subtraction games. But before we talk about aperiodic subtraction games, we need to define aperiodic subtraction games. To do that, we need to define subtraction games. To do that, we need to define games. So let's start by defining games. So by a game, I'm going to mean an impartial combinatorial game. There's a few equivalent definitions of. So it's going to be a game with two players. And it's going to have positions indexed by the non-negative integers.
So for every non-negative integer, there is a position?
Yes. If it turns out your game only has finitely many positions, all the positions after a certain point can just be null positions that you can never move to, and you can decide how you move from them because it doesn't matter. So the positions are indexed by non-negative integers, and for each position, there is a set of positions with smaller indices that you can move to. Particularly, you cannot move from the zero position.
Strictly smaller.
Strictly smaller, yes.
Nathan, it's not unified in general game. It's an impartial combinatorial game.
Yeah, I'm getting to the impartial combinatorial part. Because it's a game with two players, and then the players are going to take turns moving to legal positions until they
Oh
can.
yeah, in general, the game can have any position.
Yes,
The one
but
of
then
those
you
didn't count the ball. Okay.
yeah, I'm just making these assumptions without loss of generality.
Okay.
Okay, so in a set of smaller positions, so for each position, there's a set of smaller positions you can move to, and then the players take turns making moves, and then whichever one can't make a move first loses. The players take turns moving legally, and then the loser is the first player unable to move. In particular, such a game must last a finite amount of time because every time you move, you decrease the index of the current position. So along with games, we need to define n and p positions. So a p position is a game where the next player to move with perfect play will lose. And the P stands for previous because the previous player wins. And then an N position is not a P position. It's one where the next player wins. So this is a position. And then for a game, we can define the Sprague-Grundy function on the positions. Actually, before we define that, we need to define the max. We're going to need to use that. So for a set of non-negative integers, max of A max standing for minimal excluded element, is the minimum non-negative integer not in A. So for example, max of 0, 1, 3, 4, 7 equals 2. Because it contains a 0, it contains a 1, it does not contain a 2, and then we don't care about anything after that because it didn't contain a 2. So now we can define this function. So it's a function f from positions which are indexed by the non-negative integers. And it's also a map to the non-negative integers. And it's defined recursively. Or f of n, where n is the index of some position, equal to the max of f of I, where I is legally reachable from n in one move. So the Sprague-Grundy function has a number of important properties, but the most important property is that it equals 0 if and only if the position is a p position, which is why we're interested in this function. And from this function, we can define the nim sequence of a game. It's just the sequence of Sprague-Grundy values. And f is the Sprague-Grundy function. So now we have all this theory of general games. Let's define subtraction games. So to go from, yeah.
Do we need to say like what it is? Have you said what Sprague-Grundy is on the losing positions or something?
Well, it's 0 on position 0 because you can't move from position 0, and the max of the empty set is 0. So this thing is a self-encompassing base case.
Okay.
So to go from games to subtraction games, what we're going to do is restrict the possible legal move sets. So a subtraction game on subtraction set S, where S is going to be a set of positive integers, so it can't include 0. And this is going to be the game where from position n you can move to position n minus s for some s in s with s less than n, and you can't do anything else. So it's on subtraction set S is the game where from position n and you can move to position n minus s for s in s, s less than n, and no other moves. So it's a restriction on legal moves. So I'm going to give two examples of very simple subtraction games. So first example is one pile nim. This is the game where, because you could think of a subtraction game as you have a pile of n counters and you can take some number s counters where s is in your set. So in one pile nim, the rules of nim are you can take any number of counters from any one pile. So if there's one pile, you can just take any number of counters. So s is equal to the positive integers. And for this game, the Sprague-Grundy function is extremely easy to describe. F of n is equal to n for all n in this game. So in particular, the nim sequence is 0, 1, 2, 3. And I didn't think to look up ahead of time what sequence that is in OEIS, but I know it's in there.
827.
Okay. Thank you.
27? So 0, 0, 0, 0, 0.
Sorry. This one might test your knowledge a little more, but not too much more. The sequence is still very easy. So the second example I like to call the take one counter game. So in this game, you're given a pile of n counters, and on your turn you must take one counter. So S is the set 1. So in this case, well, the position 0, you can't move, so f of n is 0. F of 0 is 0. Then f of 1, you can move to position 0. So you can move to a position where that has f equal to 0. But you can't move anywhere else, so f of 1 is equal to 1. And then by similar logic, f of 2 equals 0, f of 3 equals 1, so you end up with f of n is equal to n mod 2. And the nim sequence, it alternates between zeros and ones. Again, in OEIS, not sure of the number off the top of my head. Okay. So these are subtraction games. So now let's discuss some things that are known about subtraction games. Most of the things in this portion of the talk are things that are referenced in Winning Ways by Borlekamp, Conway, and Guy. And the first result is going to be that if S is finite, then the nim sequence of the subtraction game with set S, which I'm just going to call the nim sequence of S because it's intrinsically a property of S, is eventually periodic. So to prove this, we're going to observe that the maximum over n of f of n is at most the size of S, because the max of a set of a certain size can never be more than the size of the set. So we're going to let k equal the size of S and let S equal to the maximum element of S. And then we're going to construct a directed graph G. And this is going to be a graph on S tuples of integers from 0 to k. And it's going to have out degree 1. And the edges are going to be, it's going to be, every vertex will have exactly one edge going out of it. And it'll be that A1, A2, AS goes to A2, A3, AS, and then the max of, and this is over T and S of AS plus 1 minus T. So in this graph,
What was the max of what?
the max over elements of the subtraction set of AS plus 1 minus T, where T is the element. So these elements will be some of these. So we're thinking about this as just a the suffix of the nim sequence so far, and then this will be the next term in the nim sequence. And since S was finite, we can always figure out the next term of the nim sequence just by looking at the previous S terms. So we have a directed graph with finitely many vertices without degree 1, and this process amounts to walking on the graph if we start at A1 through AS being the first S terms in the nim sequence. So we'll eventually reach the same vertex twice by the pigeonhole principle, which means we're going to enter a cycle, and that cycle is an eventual period of the nim sequence.
But it gives you a very bad upper bound.
Oh, it's a terrible upper bound.
You can probably improve on this.
So it's the right pigeonhole principle. So most small examples turn out to actually be purely periodic. By a lot of measures, the smallest set that gives a not purely periodic nim sequence is the set 247, which has a prefix of length 10 followed by a period of some length. And also the periods are usually very short for small sets. But once the sets have elements bigger than 10 or so, or have size more than 4 or so, this behavior becomes a lot more complicated and a lot less is known. But one thing this does show is that for every finite subtraction set, we can decompose the nim sequence into a prefix and then a period. And we're going to use this fact a lot later. So for any finite subtraction set, the nim sequence has a prefix and then a period. We're going to assume the prefix has minimal length. So now we see, so for every finite subtraction set, the sequence is eventually periodic. But then there was the case of one pile nim where the subtraction set was infinite, but the sequence was unbounded. And unbounded things can't ever be periodic. This raises the question, does there exist a subtraction set, which will not be finite, such that the nim sequence for the subtraction game with that set is both bounded and aperiodic? And then another question is, if so, what's the upper bound? What's the smallest we can make the upper bound? All right, will people be able to see if I write over here? All right. So the first thing we're going to show is that we can't have the upper bound be 1. It'll have to be at least 2. So this is a theorem due to Ferguson. It's stated in Winning Ways, which is that for any subtraction set, so now we're going to let little s equal the minimum element of the subtraction set. We have, so f is still going to be the Sprague-Grundy function. F of n is equal to 0 if and only if f of n plus s is equal to 1. So the zeros and ones come in pairs, and they're separated by the minimum element of the subtraction set. And the proof will be by minimal counterexample. So the first case, we're going to assume we have f of n equals 0, and f of n plus s not equal to 1. So f of n plus s is not equal to 1. It's also not equal to 0 because we can subtract from n plus s, we can take s counters and get to this position, which has Sprague-Grundy value of 0. So we can move to a position with 0, so it can't be 0. And so, since it's not 1, there must be a legal move to some position where the Sprague-Grundy function is 1. So there exists a t in s such that f of n plus s minus t is equal to 1. But then, from this position, we can remove s counters, because s is in our subtraction set. And when we remove s counters, the Subtraction value was 0 because we assumed that n was a minimal counterexample. But since f of n minus t is 0, f of n can't be 0 because we can legally move here from n. So this contradicts f of n equals 0. And now we play a similar game if it's the other one that fails. So if f of n equals 1 and f of n minus s is not 0, then f of n minus s has to be, you have to be able to move to a position that's 0. So there exists a t such that f of n minus s minus, this is t and s, such that f of n minus s minus t is equal to 0. Otherwise, this would be 0. But then f of n minus t is equal to 1. And that contradicts f of n equals to 1. And that proves Ferguson's theorem. And this immediately implies that we can't get an upper bound of 1 in such a sequence, because this implies that every nim sequence that's only zeros and ones has to be purely periodic. And the period has s zeros followed by s ones, and then that repeats forever. So if we start searching for an nim sequence that's only zeros and ones, we'll be out of luck. But this is experimental math, so let's experiment and try to find a subtraction set that has an aperiodic bounded nim sequence. So we're going to try to build a subtraction set. So we can start with 1. We're going to start with 1. And then it turns out that we're not going to want to throw in 2 because we're trying to minimize the upper bound. And it turns out if you throw in 2, the only nim sequence that contains only zeros, ones, and 2s that you'll be able to obtain is periodic with period 0, 1, 2. So we can't throw in 2. And throwing in 3 seems counterproductive just because the nim sequence of 1, 3 is the same as the nim sequence of 1. So we're going to start with 1, 4. And 1, 4 has nim sequence it's 0, 1, 0, 1, 2, and I'm going to borrow this notation from combinatorics on words to denote you take this and repeat it forever. So we have this nim sequence with 1, 4. So let's try a greedy algorithm to extend this. And one thing to note is that the period here this is a purely periodic sequence. We're going to try to maintain the property that we have a purely periodic sequence. That way we can analyze the limit. Because if we start getting prefixes, they start growing and containing things that we can't control, and we don't want to deal with that. So we're going to try the greedy algorithm where we start with S, which will be a finite set with a periodic nim sequence. And then we're going to let little s be the maximum of big S. And we're going to find the smallest t larger than little s, such that a few things happen. S union t has periodic nim sequence. But it could have happened that S union T is periodic nim sequence because it has the same nim sequence as S. We want the nim sequence to grow because we want to eventually get something aperiodic. We don't want to stabilize on a period. So we also want S union T has a longer nim sequence than S. So when we have these two properties, we can then add t to x. One thing you should be thinking is, why should such a t exist? And a priori, it doesn't appear to be a reason why such a t exists, but it turns out that it does. And if we just try to run this algorithm, we get the following set. We get 1, and then we get 4. The next element is going to be 7, and then 10, and then 13. So these are the numbers that are congruent to 1 mod 3. And then what sequence of periods do we get? So the sequence of periods. So we get 0, 1, 0, 1, 2, and then we have 0, 1, 0, 1, 2, 0, 1, 2. Then we have 0, 1, 0, 1, 2, 0, 1, 2, 0, 1, 2, so on and so on. So the periods are growing, as we needed them to, and they're also still purely periodic. But there's a problem. We were trying to do this to find something where the limit was aperiodic. But in this case, the limit is not aperiodic. We ended up with the suffix that we were tacking on was the same every time. We don't want that to be possible. So let's modify our algorithm a bit. In order to avoid this, it'll be sufficient to require that t be greater than 2s. That way we can't accidentally end up tacking on a suffix of the original thing, because a suffix can't be longer than the original thing itself. So when we do that, we actually get an interesting sequence. Run the new algorithm. The set we get.
So the only modification is t greater than 2s.
2s. So the new set we get. It starts 1, 4, 12, 28, 73, 163, 343. And we also have the corresponding sequence of periods. I'm just going to write the sequence of period lengths because I don't want to write down the periods. But the period lengths are all just one more than this. So the period lengths, I'm going to put 1 here because we can start with nothing here, and the period of empty subtraction set is 1. So 1, 2, 5, 13, 29, 74, 164, 344. So these are all just 1 more than that because we have the same phenomenon that happened over there, where the period has length 1 more than the largest element of the subtraction set, which is a nice property to have. So, unfortunately, we actually I haven't been able to prove that this set continues forever. So it might not, but I strongly believe that it does. But, so looking at this as a sequence becomes a little awkward. This turns out to be the easier sequence